The order of priority of various groups in IUPAC naming is given, the highest priority being given to COOH, and then comes SO3H, then this is ester group divalent COO, then this is acid chloride group, this is amide group, and then comes cyanide, aldehyde group, ketonic group, alcoholic group, amino group, then alkene, alkyne, then halogen, then alkoxy, and nitro. Now usually we come across COOH, then CN, CHO, COOH, NS2, double bond, triple bond, then halogen, then nitro group. Now a simple application of this priority in alcohols and simple compounds. Now this is CS2 double bond CH, CS2OH. Now this compound is an unsaturated compound, hence we use the prefix propene, and the last letter E is avoided. Propene, propen, that is the prefix used, and we start numbering on carbon 1 because priority of OH is higher than the double bond. So OH comes here in priority and double bond comes next in priority. And the numbering in the order of priority of groups, the double bond starts on carbon 2, hence prop 2N, En, the last letter is avoided. You can add the last letter also, 2En or 2N, then 1 all. Now here a 3 carbon chain connected to chlorine. Now double bond is given preference because halogen comes after double bond. So start numbering here 1, 2, 3, and this is 3 chloro prop 1 E double bond. Now then amino group comes after OH in priority, so OH has the higher priority. So this compound, the parent is ethane, and number 2 is given to the carbon connected to the group of less priority, that is amino group. So it is 1 all, 2 amino, ethane, 1 all. Now one thing to be noted here is that the lowest set of locating numbers is also observed during naming if the locating number of OH is the same in both directions. So if the OH group has the locating number in both directions that's same. So an example is this compound. Here if we start 1 here, then 2 and 3, the locating number is 2 for OH group in both directions. Then if we are numbering in this direction, the locating number of amino group is 1. So this numbering is preferred because if you are numbering in the opposite direction, the locating number of amino group is 3. So we select the lowest possible locating numbers. So 1 amino, propan, 2 all, that is a compound. Then another simple example, aniline, YNE, and there again is butane, the last letter is avoided. So but 3-ine 2 all, because OH group has got higher priority over triple bond, hence numbering starts here 1, 2, 3, 4, and triple bond starts on carbon 3, hence but 3-ine. Then on second carbon there is OH, so 2 all, then on second carbon there is a methyl, hence 2-methyl. Then the parent is butane, so 2-methyl but. Then the locating number of triple bond, that is 3, because on 3 the triple bond starts. So 3-ine 2-ol, 2-methyl but 3-ine 2-ol. That is. Now coming to the methods of preparation of alcohols. Now the first method is hydration of alkene in presence of dilute acid as catalyst. And dilute acid contains excess water. Now double bond breaks, so that the pi bond breaks and the charge splits, and here one portion, that is H as H positive, will be connecting to one carbon with its valency, and OH as OH negative will be getting connected to another carbon with its valency. So we get CH and COH. Now this addition is in accordance with the Markovnikov's rule. So when we take an unsymmetrical alkene, that means when we place a mirror here, this portion is not the image of this portion, or this portion is not the image of this portion. So it is unsymmetrical alkane. Now HOH addition occurs, and here H is the positive part and OH is the negative part. So negative part of the addendum, this is addendum, HOH is the addendum, goes to the carbon connected to the least number of H atoms. Only one H here, so OH goes to this carbon and H goes to this carbon, and we get this compound, that is 2-propanol as the major product and 1-propanol as the minor product. Now this reaction is catalyzed by acid, dilute acid. Now you have to study the mechanism of this reaction, and the mechanism involves 3 steps. Now acid can donate H positive, and in dilute solution there is excess water, or water is the solvent, and so H positive is reacting with a molecule of water. The lone pair of oxygen being donated to H positive, we get H3O positive, H3O positive, and this ion is called hydronium ion, and this ion is acting as the electrophile. Now H3O positive approaches the pi bond, then this positive oxygen may be connected to this pi bond, but positive oxygen does not have any vacant orbital into which the pi electron pair may be received. So the pi electron pair is received by a hydrogen, which becomes H positive by shifting of this pair of electron into the orbital of oxygen, thereby neutralizing the charge, because this oxygen gets the share of electron of this hydrogen. So we get, by shifting of this bond or oxygen, H2O, that is not a molecule. Now we assume that this line rotates through an angle of say 90 degree, and then it comes in between H and C. So this bond will be shifting towards the vacant orbital of hydrogen produced by shifting of this pair of electron. So we get SH bond. Now during this shifting of pi electron pair, the share of this carbon is lost, so that the orbital of carbon is left with no electron. It is vacant, a vacant orbital of carbon and a positive charge. Now this is the carbocation. So that is the first step, that is electrophile H3O positive attacks the alkene, and electrophilic attack of hydronium ion on alkene to give a carbocation. That is step 1. This mechanism you have to study because it is given in the text, so you study it. Now then the second step involved a nucleophilic attack of water molecule on the carbocation. Now in this medium, dilute acid medium, water is in excess, so water can function as a nucleophile, and then it reaches a positive center, that is the positive carbon, and it is having a vacant orbital, and into this vacant orbitals this lone pair of oxygen is received, so that one electron of oxygen goes to the carbon, and we get positive charge over oxygen and a bond between carbon and oxygen. So nucleophilic attack over carbocation results in the formation of the species. It's again an oxonium ion. Now when one H positive is removed from the ion, we get free OH group. Now for that removal of H positive, another molecule of water attacks the H here, so that one electron pair is donated to H, and simultaneously the electron pair in the OH bond is shifting over this oxygen, in the sense the orbital of oxygen withdraws completely the pair of electron that is share of this hydrogen also, so that it gains an extra electron, so that the positive charge is getting neutralized. So H positive combines with the electron pair donated by oxygen of water, then H positive gets bonded to oxygen, we get H3O positive. So they initially reacted H3O positive, it's gone out, so acid is the catalyst. So that is the complete mechanism. Involved 3 steps. All steps are reversible except this one. Now coming to an example of the addition of water to alcohol, and we can take propene as the example. Electrophilic attack of hydronium ion. Then according to Markovnik's rule, the electrophile should attack in such a way that a carbocation is produced which will have maximum stability. Now this is a secondary carbocation. It has maximum stability than a primary carbocation. So H positive attacks at this carbon. Now here the bond rotates through, say, about 90 degrees and connects the hydrogen atom. Simultaneous shift of this pair of electron into the orbital of oxygen, neutralization of this charge, creation of positive charge here. You get a secondary carbocation. You can indicate that by 2 degree, secondary carbocation, which is more stable, stabilized by the plus psi effect of 2 methyl groups and hyperconjugation from this 3 hydrogen CH bonds and these 3 CH bonds. So 6 hyperconjugation canonical structures, and so highly stable than a primary carbocation produced in the second case. Now then nucleophilic attack of water molecule on this carbocation, then production of oxonium ion, then reaction with the water molecule, liberation of free OH group, and then hydronium ion. Then the electrophile can attack the second carbon, second unsaturated carbon, so that this bond will be shifting in between this carbon and hydrogen. So positive charge over this carbon, then removal of H2O like this, CH3, CH2, CH2 positive, a primary carbocation, primary carbocation. This is less stable because there is only one inductive effect, and then the carbon adjacent to the positive charge contain only two CH bonds, so two hyperconjugation canonical structures, so less stable than secondary carbocation, and hence the final product will be a primary alcohol which is a minor product than the secondary alcohol which is the major product. Now another method of preparation of alcohol, that is by hydroboration oxidation using diborane. Diborane is having the formula B2H6 and it may be considered as a dimer of boron trihydride BH3, and the electronegativity of boron is 2 and hydrogen is slightly more electronegative, 2.1 or 2.2, some value anyway greater than 2. So that boron is the positive part and hydrogen is the negative part, hence it is called boron hydride, indicating hydride indicates negative hydrogen. Now you take an unsymmetrical alkene, then hydrogen is the negative part, goes to the carbon connected to the least number of hydrogen atoms here, so H of BH3 connects to this carbon because it is connected to the least number of H atoms. Then the remaining part, that is BH2, joins to this carbon, so we get CH3, CH2, then CH2 connected to BH2. Now then there are two more hydride parts in this molecule. Now this molecule can again react with another alkene. A BH bond is getting broken, H negative is getting connected to the carbon bearing the least number of H atoms, and boron is getting connected to the carbon containing the most number of hydrogen atoms. So Markovnich's rule is again obeyed. So B connects to this carbon, then H connects to this carbon, becomes a CH2 and then CH3. Then there is one more H here. So we can write this structure as CH3, CH2, CH2 twice BH, then a third molecule of propane. There again a BH bond breaks, H negative goes to, that is the negative part, goes to the carbon bearing the least number of H atoms. So H connects to this carbon, boron connects to this CH2. Hence we get B, CH2, CH2, CH3. Already we have CH2, CH2, CH3 twice. So the final product becomes CH3, CH2, CH2 thrice B. So that is the addition product. Then this product is reacted with the alkaline hydrogen peroxide. That means a combination of NaOH and H2O2, alkaline hydrogen peroxide, and there the chemical reaction involved may be represented like this: Cb, CH2, CH2, CH3, boron, CH2, CH2, CH3, boron connected to CH2, CH2, CH3. Now hydrogen peroxide represented as OH bond OH. Now B C bond breaks here. Simultaneously the OO bond in hydrogen peroxide breaks, so that the valency over oxygen and the valency over carbon get united to get a CH2OH group, CH3 CH2 CH2OH, CH3 CH2 CH2OH. Here also this B CH2 bond breaks, one hydrogen peroxide molecule breaks in such a way that one OH gets connected to this carbon because the valency here combines with the valency here, and boron combines with OH because boron has the valency and OH has another valency. They unite to form BOH bond. Here also the valency of the boron combines with the valency of OH. And again the third BCH2 bond is also broken. Simultaneously the OH bond is getting broken, this OH with its valency unites with the CS2 here, getting the alcohol CS3, CS2, CS2, OH, and B connects to B with its valency connects to OH with its valency. BOH bond is formed. So we have 3 BOH bonds, BOH thrice, that is boric acid, and then propanol. So hydroboration, oxidation. It is oxidation because OH group is getting added. So a group containing oxygen is getting added to the alkene structure. So it's hydroboration followed by oxidation, oxidative addition we can say. Now this is an excellent method for preparation of alcohols from alkene, and usually we get the primary alcohol as the product. Now a second method, see here, this is the second method, that is hydroboration, oxidation. A third method, that is reduction of aldehydes and ketones using hydrogen in presence of a catalyst, and the catalyst used are transition metal catalyst, platinum PT or palladium PD or nickel Ni may be used. Now an aldehyde, say this aldehyde is called acetaldehyde. Now here HH bond breaks and one H connects to this oxygen and the other H connects to this carbon, so that the pi bond here breaks. Then we get CS2OH, that is a primary alcohol, because a primary alcohol contains the group CS2OH. So CS2OH group is a primary alcoholic group, we say. So aldehydes on reduction using hydrogen in presence of a metal catalyst, a transition metal catalyst, gives a primary alcohol. Always aldehydes on reduction give a primary alcohol. Then there is another branch of compounds related to aldehydes. They are called ketones. They contain the CO group with divalency. Now one example is that of CH3COCH3. It may be called propanone or acetone. There again the pi bond breaks, HS bond breaks, oxygen connects to one H and carbon connects to another H. We get CH3, CHOH, CH3. Now this CHOH group, we have seen earlier that CH2OH group is called a primary alcoholic group. Now CHOH group has two valencies. It is called a secondary alcoholic group. Then there is another group called COH with the three valencies. It is called tertiary alcoholic group. So a secondary alcohol is obtained always when a ketone is reduced using hydrogen in presence of platinum or palladium or nickel. Now other powerful reducing agents are there. Lithium aluminum hydride is the most powerful reducing agent in organic chemistry, and there is a mild reducing agent called sodium borohydride, and these reducing agents also may be used for reducing this aldehyde and ketones to the corresponding alcohols. And lithium aluminum hydride is such a powerful reducing agent that it reduces acid to primary alcohol. So CH3COOH, this acid is acetic acid on reduction using lithium aluminum hydride, LiAlH4. Now this hydrogen is remaining as H negative. We get the corresponding alcohol, that is ethanol. Now sodium borohydride cannot reduce acid to alcohol, but it can reduce aldehydes and ketones to primary alcohol and secondary alcohol respectively. Now let us see simply the mechanism of action of lithium aluminum hydride on a carboxylic acid. First of all, I'd say you need not study this mechanism. Just for the sake of knowledge, I'm discussing this. Now, in acid, the OH bond is ionizing as O negative and H positive. So, H positive from this acid and H negative from aluminum hydride will combine, and H positive and H negative can combine to give H2, that is hydrogen gas, so that we get RCOO negative and AlH3. Now there is no charge over aluminum there, and this acid anion O negative combines with the aluminum. Now a lone pair over oxygen has now 3 lone pairs. One lone pair of oxygen is given to aluminum, so that 1 electron is given to aluminum in excess. So aluminum gains a negative charge and oxygen bonds to aluminum, and the negative charge of oxygen is lost when a pair of electron is donated to aluminum. And so we get RC double bond O AlH3 negative. Now this AlH3 part will donate one hydride to the carbon of the carbonyl group of the acid. So this is written as RC double bond O bonded to O bonded to Al. Then there are 3 H atoms. One ALH bond is shown here, then 2 ALH bonds are there. Now you simply assume that this bond or this line is rotating in between the carbon and hydrogen. Now aluminum is already having a negative charge. When this H with the bonding pair of electron moves to the carbon, so that this bond ultimately moves in between this carbon and hydrogen, the share of aluminum is also lost, so that the charge over aluminum becomes 0. That is one thing. Then simultaneously the CO bond polarizes in this direction, ionizes in this direction, so this becomes C positive and O negative. And when H negative combines with the C positive, there is neutralization, mutual neutralization of charges, and we get a CH bond and O negative. Now oxygen has 3 pairs of electrons around it. You need not worry about the pairs of electrons around oxygen. You simply assume that the negative charge indicates a pair of electron, and this negative charge or pair of electron becomes a bond pair here, and simultaneously this bond breaks in the direction of oxygen. So when this pair of electron, we start the arrow from the negative charge, that means a pair of electron over oxygen forms a bond here, and when this bond breaks in this direction, we get a positive charge here and there is a negative charge. And when this lone pair becomes a bond pair here, 1 electron is given to this carbon. It was already positive due to removal of this pair of electron. The charge over this carbon neutralizes, and again the charge over oxygen neutralizes when the lone pair over oxygen shifts in between oxygen and carbon. That is indicated by starting the arrow from the negative charge to a position in between carbon and oxygen. So removal of this OAlH2 part as OAlH2 negative. So what we get is RCOH, and this is an aldehyde. So that first stage in the reduction of an acid is the production of an aldehyde. Now the aldehyde again reacts with the aluminum hydride ion, that is lithium aluminum hydride. Lithium is remaining as a cation. It has no role in the reaction, so we avoid Li positive. Now the carbonyl group polarizes or ionizes as C positive and O negative. Then H negative from AlH4 negative is transferred to this carbon so that CH bond is formed. The charge over carbon is neutralized by the charge H negative coming and bonding with the carbon. This positive charge created by polarization is neutralized by combination with H negative, and the charge over aluminum is now neutralized to 0. We get AlH3, which is removed, and we get HCH bond with O negative. Now in presence of acid, this O negative becomes OH, so we get RCH2OH, that is primary alcohol. So that is the mechanism for reduction of a carboxylic acid using lithium aluminum hydride. You need not study this reaction, this mechanism, but you go through this mechanism and be familiar with this mechanism, and understand that a carboxylic acid can be reduced to a primary alcohol using the powerful reducing agent, that is lithium aluminum hydride LiAlH4, whereas NaBH4, which cannot reduce a carboxylic acid to a primary alcohol, can reduce aldehydes and ketones to a primary alcohol and a secondary alcohol respectively. So that is enough. Thank you.